Today's lesson deals with calculating pH and pOH. So we need to start off with talking a little bit about what water does when it's in solution. So water itself can ionize. So if you take two water molecules, in a very, very small number of cases, what'll happen is that one of the waters will give up its hydrogen to produce a hydronium and then leave behind a hydroxide. So this means that in a solution or in a liquid that has only water molecules, you're going to have a teeny tiny bit of hydronium and a little bit of hydroxide. And it's in such low concentrations that our conductivity testers that we use in the lab can't actually detect the fact that they exist there. But they can be detected with very, very sensitive instruments. And it's been discovered that the concentration of the hydronium and the hydroxide is 1.0 times 10 to the minus 7. So think about that, 0.0000007 moles per liter in distilled water. So what happens is we can actually define whether we've got an acid or a base depending on the concentration of the hydronium and hydroxide in solution. So for example, if the concentration of our hydronium increases, it becomes greater than 1.0 times 10 to the minus 7 moles per liter. By the way, that this it kind of exists in a way that as one increases, as hydroxide increases, hydronium decreases and vice versa. So if my hydronium increases, my hydroxide will decrease and this becomes an acid. If the concentrations of hydronium and hydroxide are the same, this is a neutral substance. And if my hydronium concentration is less than 1 times 10 to the minus 7, and my hydroxide is greater than 1 times 10 to the minus 7 moles per liter, then I've got a base. So kind of based on the concentration of hydronium and hydroxide in solution. Now, the pH scale was developed as a method of expressing that H+. It makes the math, when you don't have a calculator, a little bit easier to do. And pH stands for the power of hydrogen. So that's what it means. There's also another scale called the pOH scale that expresses the hydroxide ion concentration. And so I'm going to show you how to both scales and then how to do both calculations involving hydronium and hydroxide to find the pH and the pOH. So here is the pH scale, and I'm going to start it off at 0 and end it up with 14, and in the middle is 7. Now, most of you know that 7 is neutral, and everything below 7 is an acid. Everything above 7 is a base. And we're just going to talk about some common things and their pH. So for example, battery acid can have pHs anywhere from like 0 to 1. Tomatoes can have a pH of around 4.2. Blood is almost neutral, a little bit basic. And ammonia cleaner has a pH of 11.1. You don't have to know these. Please don't be memorizing these numbers. Okay, just realize that these are just some examples. Now, we know that our acids increase in basically in concentration and strength. So increasing acidity. As you go to the ends of the line, so an acid with a pH of 0 is going to be stronger than it's going to be more like a more potent acid than an acid with a pH of 4. And the same thing as we go towards and the end on the base scale. And this is, it increases. And by the way, the word is alkalinity. So alkaline substances are bases. All right, so now the pH scale. And remember that what I talked about here, that as one increases, the other one decreases. So if I have here at the pH of 0, a very high level of hydronium, I'm going to have a very low level of hydroxide here. And so the pOH scale is actually the opposite. So here it's going to be 14, here it's going to be 0, and neutral is still 7. And here's the thing, the rest of it stays the same. So this is an acid. Acids are going to have pOHs greater than 7. Bases are going to have pOHs less than 7. And again, the closer to 0 on the pOH scale, the stronger the base. The closer to 14 on the pOH scale, the stronger the acid. So they're kind of opposite of each other or complementary to each other. And we'll come back to that later. This becomes an important aspect of something that we will talk about a little bit later on. So the next part is, how do we calculate pH and pOH? And the first thing that I want you to know is I want you to see some trends. So this first little bit that I'm going to do here is you're going to be able to, after I show you what the trend is, give me what the pH or the pOH is without using your calculator to begin with. So the first one I'm going to show you is this. So this one here, 1.0 times 10 to the 6, the pH is going to be 6.00. By the way, pH and pOH do not have units, all right? So I don't know if you guys saw or are seeing the relationship. Do you see that the pH is basically an expression of the exponent? And that's all it is. So as long as my number in front here is 1, I can look at my exponent and figure out what my pH is. So let's take a look at the second one. Hydronium ion concentration of 1 times 10 to the minus 7. My pH is going to be 7. Okay, so again, it's the exponent. And I'm sure that you can do the third one already here. So my pH is going to be 13. Now, let's take a look at my hydroxide ion concentration. So same thing is going to happen here, but instead of pH, I'm going to write pOH. So the pOH of a hydroxide ion concentration of 1 times 10 to the minus 9 is going to be 9.00. For the next one, pOH is going to be 4.00. And the third one, my pOH is going to be 12.00. Now, for the rest of my examples, I'm going to go backwards. So I need to go from pH to concentration. And so literally that's what we do. We know that this is going to be the exponent with a negative sign in front of it. So this is going to be 1.0, and I need to talk about significant digits. So bear with me now as I come up with what they are. Times 10 to the minus 3, and this is a concentration, so I do have units. Okay, don't get into the habit of leaving out your units just because we don't have them for pH and pOH. Concentration afterwards does have a unit. Please don't forget that. And this one then, 14.0, this is going to be 1 without a 0, and you'll see why here when I show you how to do significant digits with pH and pOH. All right, pOH, same thing. My hydroxide ion concentration is going to be 1.00 times 10 to the minus 5 moles per liter. Again, please don't forget those units. And a pOH of 1 is going to be 1 times 10 to the minus 1 moles per liter of hydroxide. All right, so again, you can see that we can figure out our pH or our pOH by looking at the exponent. And by looking at pH and pOH, we can actually figure out the concentration of our solution. And this becomes easy as long as our number in front here is 1. I'll show you guys how to use the formula for when situations where that doesn't occur. But before I do that, I need to talk about significant digits with pH and pOH. And this you'll find it frustrating until you get used to it, but you will get used to it. So remember that pH represents the exponent. So here is our example here, and I'm going to color code it. So this number here, I have a hydronium ion concentration of 1 times 10 to the minus 2. This number here is what we use for significant digits. So this number has 3 significant digits. We never use the exponent for our significant digits. So like I said, I'm going to color code a little bit. I'm just going to use different colors. So this number here is used for significant digits. My exponent is not. However, when I'm calculating my pH, remember that my exponent is the number in front of the decimal. Now, that doesn't count for significant digits, right? And on the pH, it doesn't count either. So this number here, to write it with the same number of significant digits as my concentration, I need to have 3 numbers after the decimal. So this number here now has 3 significant digits. So the rule is that for pH and pOH, and only pH and pOH, the number in front of the decimal does not count for significant digits, right? Does not. So if I go back to my example, you can see here, for this one, pH of 3, you can see that, I'm just going to use a different color here. You can see that I'm not counting that as a significant digit. When I go back to concentration, my concentration should have 2 significant digits. Those rules haven't changed. So moles per liter concentration, same rules apply. So I have 2 significant digits. pH of 14, these numbers in front of the decimal do not count, they're not significant. So my answer should have 1 significant digit. Okay? Same thing here if I go to the top. So this number has 2 significant digits, which means I need 2 numbers after the decimal. And I know that you're probably thinking, what? I know, but you will get used to it. And remember that this special rule is only for pH and pOH. Don't start applying it to everything. Okay, only pH and pOH have that special rule where the number in front of the decimal does not count as a significant digit. Why? Because that number in front of the decimal is representing an exponent, and exponents are never part of our significant digit determination. All right, so how do we calculate pH and pOH mathematically? And we've got a couple of formulas here for you to learn. And by the way, they are the same for pH and pOH, except that for pH we use hydronium, for pOH we use hydroxide. So here's the first one for pH. So pH is the negative log of the hydronium ion concentration. So if you've got your calculator handy, you're going to need to pull it out. And by the way, the instructions I'm giving is for a graphing calculator. You can do this with most other calculators as well. Sometimes the rules are a little bit different depending on how sophisticated your calculator is. But basically all that you do is you kind of apply this, this number. So negative log, so you're going to press the negative sign, which is underneath the 3. You're going to press the log button, which is to the left of the number 7. And then you're going to type in whatever the concentration is that you have. So whether it's hydronium for pH or hydroxide for pOH. So we're going to do our first example, 2.523 times 10 to the minus 3. So it's negative, again under the 3, log to the left of the 7, and then I'm going to type in that number. So 2.523, and then you're going to put in the exponent. And There is most of you use the little, what I call the hat, which is this to do your times 10 to the minus 3. But there's actually an exponent button that reduces your chance of error. And that one is actually found above the 7. So after you type in 2.523, hit your second button, and then the comma, which is the number above the 7. You should see an E appear in the older versions of the graphing calculator. The newer ones, I think, have 10 to the power. It shows up with 10 and then a little spot for the exponent. And then you're going to type in the exponent, minus 3. Okay, close your bracket. And you end up with the, in this case, pH. All right? So the pH here is going to be 2. Remember, that number does not count for significant digits. So what I have to do is I need to make sure that I include 4 numbers, because this number has 4 significant digits, 4 numbers after the decimal. And this becomes 2.5981. Right? Our next one is a hydronium ion concentration of 2.5 moles per liter. So again, negative log, okay, beside the 7. And then I'm just going to type in the 2.5. Now, are you seeing a negative number there? Yes, pHs can be negative. Now, in actuality, it makes them just really difficult, these acids really difficult to use, but they can exist. And so pH and pOH numbers can be negative. So this number has 2 significant digits. The number in front of the decimal for pH and pOH don't count. So this value will be negative 0.40 as a pH. Our next one, we're going to do the same thing, but of course with pOH. So again, negative log, and I'm going to type in that concentration, 2.0 times 10 to the minus 14. So I'm actually going to write the formula. And so my pOH is going to be, and again, the number in front of the decimal doesn't count. That 13 isn't part of my significant digits. So I need 3 numbers afterwards. And this turns out to be 699. And my last example for my pOH, again, I'm going to write the formula this time. So 2 times 10 to the minus 13 moles per liter. And so this time my pOH, again, the number in front of the decimal does not count. This number has 1 significant digit, so 12.7. All right? So doing the calculation is easy. It's those pesky significant digits that students struggle with. But again, with practice, you'll get it. Okay? Students do. So don't worry about that. All right. So we used our formula for calculating pH and pOH. Same formula, except that for pH we use hydronium, for pOH we use hydroxide. Again, it's going to be the same formula when we go backwards, when we go from a pH to a concentration. And so this time the formula is 10 to the power of negative pH for hydronium and 10 to the power of negative pOH for the hydroxide. So for this one here, I've got a pH of 2.34. So in my calculator, I would write 10 to the negative 2.34. And in your calculator, you will find the 10 to the power of button as a second function to the log button. So again, take a look at that log button. You can see that with the second function, you actually get 10 to the x. So again, second function, hit that log button. Then remember the negative sign, okay? So negative 2.34, and that will change it to concentration. Now, my answer that I got, and this is, by the way, completely acceptable, is 0.00 how many significant digits? 2. So 0.0046 moles per liter. You can leave it like that. That has 2 significant digits and it's fine. But you'll often see concentrations with acids and bases as written in scientific notation. So this would be 4.6 times 10 to the minus 3 moles per liter. And again, you don't have to do that. As long as you have the correct number of significant digits, you're okay. All right, our next example. So 10 to the negative 10.3. So this turns out to be, and remember, 1 significant digit, so 5 times 10 to the minus 11 moles per liter. Our next one is a pH of 2. And so for this one, again, 10 to the negative 2. And so this turns out to be, if you take a look at it, right, it turns out to be basically 0.01, right? But this has no significant digits. So basically your answer is the exponent. Okay, that's what it is. Okay, will I ever do that to you somewhere? No. I wanted to show you though how you've got to be careful with significant digits with pH and pOH. Now, last example here, 10 to the negative, oh, by the way, this should be moles per liter. Let's not forget the units. For our last one, 11.735, so 10 to the negative 11.735. And again, this number has 3 significant digits, so when I change that to moles per liter, it turns out to be 1.84 times 10 to the negative 12 moles per liter. So I hope that it made sense how to use the calculator to solve the pH and the pOH. Please remember that pH and pOH are just numerical representations of the exponents for these concentrations. Okay. Now, because the pH and pOH represent exponents, basically when we change, when we go up or down 1 pH unit, we're actually changing it by a factor of 10. So for example, if I go from pH 3 to pH 5, what's the difference in the concentration of the solutions? And so basically going from pH 3 to pH 4 changes by a factor of 10. And then from 4 to 5, it changes by another factor of 10. So this becomes 10 times 10. And so it turns out to be 100. So solution with pH 3 is 100 times more concentrated than a solution with a pH of 5. So realize that, again, pH and pOH represents the exponent of a solution with the base of 10. All right, so this is our introduction on calculating pH and pOH. Again, the calculations are easy. It's those significant digits that you've got to practice and stay on top of. So work really hard to understand those as you work through the assignment today.